Welcome to Coding with MZmine. I'm Robin, and today we're going to code like a very simple MZmine 3 module. And if like anyone who's using MZmine knows that there's modules to process spectral data. So we have the mass detection module and some filtering of raw data in MZML files and so on. We then have modules that construct feature lists, and we have modules that run on feature lists to identify compounds, to filter, to do some normalization, and so on. So if you want to create a new module, the first step that usually is very insightful is think about a module that's already there, and that's the closest to what you want to accomplish. In one way, if it's, for example, a filter, so you want to filter the feature list rows, maybe the best option might be to just add like your option as a parameter in the already existing feature list rows filter, because first, it's going to be very easy to implement. So you only have to add a new parameter, you handle it in the same task there where everything else is handled. You can look at how it's done there. And then later, once it's implemented, people are going to see it directly, even without advertisement, even without people like telling them to look for it. They already use this module. So they might see there's a new parameter and they can just like activate it and read about it in, of course, the help, which is the online documentation where you can just add it. And even if you don't find anything that's like exactly what you want to do or similar to what you do, if you find a module that's like taking the same inputs, let's say, you can look at the parameters, you can see how can we get the user input, how can I process, how can I get the result that is very similar to the module. Yeah, so in this case, we are just creating something completely new. So we're just saying that for a feature list and a feature list here, we have to understand that a row is a feature list row, like just from the data structures in MZmine. We have the feature list, we have a feature list row, and then for each sample, we have a feature. Yeah, so for each sample, a feature, and then a row just makes up multiple samples, so multiple features, and then we have the average values that are constructed from like all the samples. So we have the MZ, retention time, and so on as the average, and then we have the MS2 fragmentation spectra that come from like different samples. We also collect them into a list that is for the feature list row. So if we start from here, in this like short video, we're going to create two new columns in the table for the rows, like assessing the quality of spectra based on spectral entropy, which is one measure where people use to just look at the spectra and the chaos in spectra. So how can we do this? Going to like back to MZmine, we're going to use like the IntelliJ IDE here. You can use any other tool to program for MZmine. We have some tutorials for different ones, but like most of us, I think now use IntelliJ at least. Um, you see that I have different remotes set up. You might only see your own remote. I strongly encourage you to also add the MZmine remote, because then we can just pull all the latest changes to the MZmine repository, and we don't have to make sure that my master branch is actually up to date, because there's a lot of changes happening on MZmine. So, and then I always create a new branch locally from the MZmine master. So I do new branch and then spectral entropy. That's what we're going to work on. And now, looking at like what kind of module we want to create, I might just, double shift in IntelliJ. I could now just search for like all the different tasks that are in MZmine. There's, for example, the CCS calculation task, which we just saw in the feature list processing. So for this one, if I just like control click on here, I directly jump into the tree structure of the project. And you're going to see I don't really navigate that much in the tree here, because I can usually search for things way faster than I can find them. We do have, of course, some like structures. We have modules, and then like data processing, data analysis, input and output. Um, but so if I want to navigate this, I usually just click here, or I like double shift and search for something, or I like control shift and F to search for, let's say, like the CCS calculation module. So you can see, like, I can find all the different things like very quickly by just searching for it. And so how do we start now? Of course, we can just create all the classes by ourselves, or we can just copy one of the modules that we already know. But we also have some examples here. Those are like very bare examples of like how you can start with a new module. But a very good one is if you like work with feature lists. This one is like the minimum setup to work with a feature list. So I'm just going to copy those classes here. We always have the module, parameters, and the task. You can also look at the different implementation of task here. Maybe there's some like one that's more matching to what you want to do, but it's usually easy to just go from here and just modify it slightly. So data processing is usually where most of the feature list processing happens. And now we just have to create a new folder. And so let's do new package in the data processing. It's going to be spectral entropy. And then in here, oh, I should actually give it like a prefix. So let's say it's a filter because it could be used as a filter downstream based on the spectral quality. So I can refactor the name, and it already exists. Let me see. Spectral entropy. This one is unfortunate. I already tried out at one point, so I'm gonna just delete them. But that just means I already have the package. So let's find it again. Spectral entropy. And in here, we're just going to paste all the classes that we just copied. So we have the empty featureless module and empty featureless parameters and task. These three classes you will usually see for mostly everything that we do in MZmine. So I can open the module first. Module is very easy. Like this one comes with some descriptions so that you don't forget that you have to register the module in the main menu so that people can actually also use it. That you might want to register it in the batch mode module list. So the batch modes is where people can just like set up their pipeline and they can run it automatically. And then down here, there's some other things that we can define. So we can start by defining, this one is the spectral entropy, like calculate spectral entropy. And then as a description, calculate spectral entropy of fragmentation spectra in feature lists, right? And if we scroll down, or like let's start from the top. We have a class featureless module. Then we have the MZmine processing module, which is just like the super class or the super interface in this case. And this interface just forces us to describe, like to implement some of those methods that are like vital to the whole structure in MZmine. So we have to define how to run the module. We have to define what the category and the description and so on of this module is. So going back here, we have the name and the description. We already specified it here. In this case, we're just gonna return those values here. We have the parameter class, which is this parameter class here. So we're going to change the names in a second. And then we have the module category. If you want to see like the module category, you can just hit Control Space. And then featureless filtering, I think, for now is sufficient. So we're going to input a feature list. We're going to process something and maybe do some filtering later on based on that. And then in the run module, we already have some basic implementation of how we want to run the module. And this method is always called when people open the dialog. So if we are in MZmine and we open, let's say, the feature filter, it's opening the dialog. And if I now click OK, and I did set up everything and it starts running, before it like actually schedules the job and everything, I click on OK and I jump into the run module method of this module. Yeah. So we're going to have the project, which is the current project of MZmine. We have the parameters that were set by the user. We have a list of tasks, and this list is only a list that is then passed to the task manager. So we don't have to worry about scheduling tasks. We just have to create them. We can decide like how many tasks we want to create in here. And because we're working with feature lists, it's very easy to say, okay, we have, let's say like 100 feature lists for each individual raw data file. We might have a feature list, and then we want to run the task individually. And the tasks don't interfere with each other. Like they don't interact. We don't share information between the feature lists. So we can just run one task per feature list. Yeah, so that's a very common way how we parallelize in MZmine. There are other ways, like there's other modules, like the spectral library matching, for example. It just uses like all the feature lists that it gets, and it gives them to one task, and then we do the parallelization internally in this task because we have to prepare some information beforehand. Like we have to import the spectral libraries, we have to make sure they're there, and so on. So there's these two options: one task for all, or like one task for each feature list or each raw data file that we want to process. So, and we can see here, there's already a way how we can get the parameters. And so how do we get the parameters, or how do we define the parameters? Let's first change all the names and then go through the other classes. So I'm just going to hit Control Alt and R for renaming. That might be for my IDE, so you have to see how you set it up. So feature list module. So we are going to call it feature spectral entropy. Let's say feature spectral entropy module. I think that should be sufficient. So we can copy the rest and refactor. We can rename the other one. So again, Control Alt R and change all the names. Refactoring here shows again like one of the strengths of Java. So because we already we have a strong typing system, we also do refactor and rename all the instances where we refer to these classes in other classes. So now we actually say the parameter class of this module is the feature spectral entropy parameters. We can look into this basic implementation that we just copied, and it just defines one public static final feature list parameter feature lists, and we create one new instance. There's two important things here. It has to be public static and it should be final, so that's always set. If we need more parameters, we can just do the same thing. Like we can say public static, okay, static final. And let's say we want like a true false Boolean parameter. We can just say Boolean parameter and then, bool, yeah, it's wrong, but like this. And then usually we have to define the name and a description. Yeah, so we would always like type in the like bool and some description. And it's very important that the name of the parameter actually stays the same, because the name is going to be the key for us to get the value from the parameter set. So later on in the task where we do the logic, we're going to extract the value by using the parameter here and by using effectively the name. So again, we have a public static final. This is important. And then we just you can copy parameters from other modules where you know you're using the adduct, or you're using like an MZ tolerance parameter, retention time tolerance, you can just copy that from somewhere else, or you can just search for them in the parameters package, like here. And then we have the feature lists. And in this constructor, we could actually define that our module only runs on one feature list as a maximum, so that it only runs on one. Or we could also define a different name and description if we needed it. But because this parameter is used throughout MZmine and it's a standard parameter, we actually have an empty constructor with default parameters. So the name and description are always going to be the same throughout the modules. And then in the constructor of this specialized parameter set, this parameter set is just one parameter, yeah. We just pass in super new parameter array, like a list of parameters, and we pass in the feature list, like this one parameter. And this is because the simple parameter set actually has a whole bunch of logic, how to get the parameter, how to get the logic, and so on. We don't have to define it here, we just have to pass in all the values that we want, and then MZmine is going to auto-generate a dialog, and like each parameter has a component, users can select values, there are some default values that we can set, and so on. So we have the parameters already defined here. For this module, we actually don't need more, so we can go back to the module, and then in the run module, we can define how to run the logic. And so we are going to create a new feature spectral entropy task. We're passing in some information, the project, feature list, the parameters. So this is already some information that we extracted from the parameters. We're still going to pass in the parameters because that's going to be used in here as well later. And then in this case, we also pass in some default values here for the when we call the module, and the storage I'm going to explain later. We add it to the list of tasks, and it's going to be automatically added to the task manager and scheduled later. So we can focus on the task and the actual logic. In here, you will find already some like preset things that are very useful. So for example, we have some fields where we just pass from the constructor, we just pass the project and the feature list and the parameters. We just pass to the fields that we have in the task. Yeah, so each instance is going to have different parameters, maybe different feature lists. We start off with a finished and total rows. So to just keep dibs on the progress that we make. And then when we look at the structure here, there's already some structure defined because we extend the abstract task. Yeah, so abstract task is also already defines a lot of logic here. We don't have to use all of that. I can show you how it looks like when we were to create like a completely empty task. So if I just say my task, and then I say extends abstract task, it needs to be the one from MZmine, of course. IntelliJ is always going to give you some hints that you're missing something, or that you might be able to automatically generate some code. If I hit Alt Enter in IntelliJ, it's going to give me some refactoring options. I can also just hover and just click on this thing, but Alt Enter, and then it says implement methods, because abstract task is actually forcing us to implement and to fill those methods with logic. So we would get these three methods, which is the task description, which you always see in the task manager on the bottom. And then the finished percentage, of course, showing you the progress. And then we have the run method. And the run method is the actual logic. Because all of this is already defined, we can go and change this task. And I think it's very good because it already has some hints on what you should do and what you need. And one more thing, if we hit Alt Enter again, we usually need a constructor to create a new instance of my task. So if I do this, I just overload the constructor from abstract task. And in this constructor, we already need a storage and a module call date. So this is the only two values that I have to pass in my task to actually make it work. And just one thing like Java related, and even for people who are new to Java, that's going to be like very different, right? But people who do Java a lot might not use annotations at all. Like this one is just an annotation. It's optional, but we decided to use them like as much as possible. So we're going to annotate that the storage might actually be null. So storage memory mapping in MZmine is used only to store like heavy data, let's say like the spectral data from raw data files, from mask lists. Then we have the feature data, and we're storing it on a fast local drive to offload it from the random access memory, from the RAM. Yeah, so that we have more capacity to run actually processing in the memory. And it might be null because our module might not generate a lot of data that needs to be retained. And if this is null, we don't retain any like data on disk. We just do it in memory. So, and then the module call date always needs to be not null. So if we see this annotation, we can just directly assume that module call date is not null. So we can call methods on it like toString, we can map it to something else. We don't have to do a null check here. Like we don't have to actually get into this and like always check for null. Yeah. I guess it's also gonna, yeah, it's also gonna give you that the condition is always true because this is already a condition that we set. So that's a nice way for you to annotate variables and people are gonna know it's null or it's not null. And then you also have to stick to it, right? So I'm going to delete this one, but then we go back to the task here. I'm gonna clear up my mess up here. So from the task, we're now gonna implement some logic. First, we have the constructor again, so this one might be null. Then we have the project and the feature list and parameters. And then usually, if there are more parameters, we can call getValue and then get any value from the parameters. Right now, there's only one parameter, and I can just go feature spectral entropy parameters. You can see I don't actually type that much. You can just hit Control Space also to get some auto completion. And then in here, because the feature list parameter, which we defined in the parameters class, was public and static, I can actually directly access it from the class. So I can access and then use it as a key to gain access to the value. And because Java is like a strong static type language, we also get the type of the value directly. Yeah, so this one is a feature list selection. And from the feature list selection, we can now get like all the methods and we can directly say, get the matching feature list. We can define a variable and get all the feature lists here and so on. Because we already did that in the module, we don't have to do it here again. Like we already have the feature list here. And we can directly start working off of the input that we got. So what we have to define is the task description, runs task on feature list. So the name of the feature list, we can say calculate the spectral entropy on the feature list. Then we have the task with the logic. And down here, we have the get finished percentage, and it's already filled in with like the standard workflow, like standard approach. So we have the total rows equals 0. So if the total rows equal 0, then we return 0 progress. And otherwise, so else, we divide the finished by the total rows. If I were to write this, so I mean, I could do something like this, right? This and then return 0 to just avoid the division by 0. And then else, we're gonna do finished divided by total rows. The nice thing is that usually your IDE will already warn you that something is wrong with this code. it looks correct, but it's actually wrong because we do want to get a double value, but those two instances here are both integers. Yeah. So if I just Alt Enter, it gives me inspection, integer, division in floating point context options. Okay, so I do divide an integer by an integer. This will result in an integer. That's a thing that's true in Java, and it's also true in some other languages. So the way to get around this is to just cast one of those values to a double, because then I'm in a floating point, like a decimal context. And then again, with like this if statement here, because it doesn't look so nice, and if I actually perform like the auto formatting that I have in IntelliJ, I actually generate so many lines of code for just like something very simple, like total rows equals to 0, then 0, and else this. So this is just like an inlined if or else. And I think it's a very nice way, at least for those simple statements, and it's very expressive. So this way we get the finished percentage, we have the description. We're going to go through the run method. It's very important that first we typically want to set the status of the task to processing, because if we reach this point here, we know that the task manager actually started the task. So there was a like free thread, and we started this task, and now it's running. So we should change it to processing here. We can log some information. So it's automatically going to log something like, oh, we started this module at this time, and so on. But if we want to log some more information, we could now say calculating. I think honestly we could just do get task description here. Let's see. So we could just log the task description here and just do that. And then usually in the logic we would first kind of like set up everything. So we have the total rows need to be defined as the feature list, and then get number of rows, for example. And then we can apply some loops. And in those loops, it's usually a good idea to actually check if the user canceled the job. So if the user is canceling it, we don't want to finish. We want to directly like return and stop the process. Yeah. So this is usually what we do. And then after the row is done, after we do some logic, so we gonna insert logic here, we're going to just update the progress and by incrementing finished. And then later we're going to add an applied methods to the feature list to keep track of what we're doing with the feature list. We're logging something, and then we're setting the status to finished. So let's get rid of the logging here. I think it's already going to log it once we set it to finish. So one thing for the applied method, it's very important that we don't forget this. So we have the feature list, we add description of applied task. It's a very simple thing. We create a new simple feature list applied method. We have to define the module here. And again, it has a correct name here because we just refactored the names of all these classes. We give it the parameters and the module call date. So once, if we have a feature list here, we can right click, show the feature list summary, and we see all the applied methods down here. And we can even create a new batch queue by just clicking on this, and we have all those modules here with the parameters, with everything. So if we forget this, user's not going to be able to generate those automatically. So this is the usual way to do it. And so now we can get to the logic. And logic is just going to mean that, just looking at this, so the logic is just going to mean that for each row, we get the fragment spectra, and then we're going to calculate the spectral entropy and add a new type to the feature list. So rho dot, let's say if rho has fragmentation. So we could do this first, and now in here we can now, for example, say process row, and then row, and generate a new method to just process one of these rows. Or let's do it a different way. We first implement it and then we extract the method to actually show what it's doing. So from here we can say row get most intense fragment scan. So there's a feature list row. We get the most intense fragment scan from all the samples. It's one list, and we just get the one with the highest TIC here. That might be not like the most suitable case, but it's a very easy way of getting one mass spectrum. So we can do scan of this. And then to calculate the spectral entropy, there's already some methods. If we look at scan utils, for example, there's some methods that we can apply, and get spectral entropy, for example, gets us the spectral entropy of a scan. So we can just create the variable. If that's too fast, I'm just doing Control Alt and V for generating a variable for the thing that I just typed in. So we have spectral entropy, and we get it from the scan utils. If I jump into here, this is all the logic that we're using. Can be implemented very easily, right? And it's only important that we put in a not null spectrum, and we get out a double value, right? So floating point number. So we get the spectral entropy, and the same we can do with the normalized spectral entropy, like this, Control Alt V, and normalized spectral entropy, and we have both values. Then from here, I would like to add two new data types to the feature list table. I have to think about the feature list table and maybe think about some types that are very similar. And what comes to mind is any score types. Yeah, so we have different score types in MZmine. There is, for example, this cosine score type, and I can directly control and click here, and it was like double shift actually. So I just click double shift to get there. And in here, you can see I still have some methods flying around. I'm gonna some classes flying around. I'm gonna delete them in here. So I'm just jumping to the score type, the cosine score type here, double shift, and this is how we define how a new column, a new data type is like stored, but also represented in the feature list table. Of course, it's going to be like a double value, so floating point number. And with floating point numbers, it's usually very important that we define some sort of like format, because otherwise some of the values might be like just trailing a lot of zeros or nines, because like depending on the precision of the actual value. So formatting the value is actually like a very important thing. It's important for the feature list, but it's also important once we export the feature list to the user. And this type then actually defines all of that logic. So we usually, for like any score type, we usually get from the preferences in MZmine, we get the score format, and then this is just the default. Like if in any case, like this would be like not available, we would get the default type. But and so how do we define a new column then? So first, we can just use this cosine score type. We can copy paste the class. We can then just call it spectral entropy. Yeah, score type, why not? And then because it's a score, right? So, and then here, spectral entropy, and score doesn't matter. So spectral entropy. This is the unique ID, and the unique ID should not change at all. Like once we define it, it should stay like this. It's an internal thing that we use to save and load feature lists, but it's also used, for example, if we export to like the feature list, we also use it as like a machine readable but also human understandable interpretable value. So it should be something that is well for both. Then here we can say spectral entropy, and we typically only capitalize it first, spectral entropy. Then here, of course, copy paste can sometimes be tricky, so remember to also change all the comments. And then the default visibility here just defines if once we compute this value, do we really want to see it like as a default in the table? Or is it more something that might be useful like downstream when people like other modules might be filtering based on this value? So I would say the default visibility here might be false. If someone applies the spectral entropy and they want to see it, they can still activate the column in the feature table, and that's also going to be retained. So we can set the visibility here. So we have the title in the table, we have the visibility, we have this as a like unique ID. We could also like Control Shift F search and then see if there's already something similar, right? Um, I think there's no data type. So yeah, there's only one data type class here that has this string. So it's a unique ID and we have to make sure it stays unique. And then we can just copy this class and paste to get the normalize. So for each column, we have to define a new type, despite, of course, this column having like the same behavior and everything, right? But is very important because we need the key and of course also the way to have like the header and the key needs to be unique. And again, we can check if it's unique, and it is. So normalize spectral entropy, normalize spectral entropy. So, and then jumping back to the task that we just worked at. So Control E gets us to this one. We can jump back to the task. And now, with the row that we're working with, we can set a data type. We can go for spectral entropy type dot class. This is the key that we have for setting the value. And here we can already see it actually expects a float value, but we have a double value. And that's gonna actually get us into trouble. Not so much though, but still, like, because we have like the strong typing system, we do know that the spectral entropy score type is a score type, which is a float type. So the float type defines that we want to have float values, which is also a floating point decimal number, like the double value, but with less precision. And that's actually important to Java, but it's also important to other languages. So if you're working with floating point numbers, the precision actually makes a difference. So if I say, let's say, if I define a value, this, for example, might be represented like, is a double value. And if I now say that 2.0 float, like 2.0 double and 2.0 float equals, it looks like it should equal, but it might not. Because this one is a double precision, this one's a floating, like float precision, so the precision is not the same. So there is ways of like just casting the value. So we can use the spectral entropy and we cast it to a float because we can just change the precision here. And we do the same with the normalized spectral entropy, also calling the different data type here. And then we can add the normalized and the spectral entropy to a row. And it should show up in the feature list table now. So this is all the logic that we implement for now. But for actually running this module, we have to go back to the module class. So let's see, it's down here. So we go back to the module class, and there were some important notes up here that we didn't capture yet. So if I just hit double shift and then main menu fxml, we can jump to the main menu, and in the main menu, we define the different modules that we want to run and in what menus they are to find. And the CCS calculation module was in the processing, featureless processing part of the menu. I'm just going to copy it for now, and we can put it here. So calculate spectral entropy is in a feature list method, so I don't have to specify it's on feature list level. I can just go out here and then just say spectral entropy module, and it's automatically filling in the rest. So from here, I can just see that it actually links the correct module. And once the user sets up the parameters, it's directly going to call the run module method, which is then creating the task and running it later in the task manager. So for now, I'm just going to import some data and do some just basic processing. So we have two samples that we import. Then in the feature list, we're just going to get to the aligned feature list here, like here. And now I can go to processing and I can find the calculate spectral entropy module. If I click on it, there's only one parameter. And the nice thing is this one parameter actually has all the components that users are already know from other modules. And we can just select the feature list here. If I now click OK, it's actually very fast because we don't calculate that much. And if I open the feature list, it's going to show me, in this case, it's going to show me the spectral entropy and normalized spectral entropy because I already did that before. So I already activated it here in the settings. If you create something new and you set the default visibility to false, you typically don't see the new columns. So you would have to scroll down here and then just change the visibility of the normalized spectral entropy column. And as you can see, the header is reflected here, and we defined it in the type, and is also reflected here, and I can now just sort and see the spectral entropy and the normalized spectral entropy here. And if I click on show and then most intense MS, I might be able to just get the spectrum, and this is the most intense MS, so it's the one that we used, and we can see that this one is the spectral entropy of this spectrum, and it was detected actually here in the orange sample. That's why the signals are orange. We do see though that usually we have more than just one spectrum, right? And another very important aspect is actually that the spectra, we usually don't use the raw spectra in MZmine. We have the mass detection module, and mass detection is used to threshold the spectrum. So to get rid of some noise, we might also use some other filters. And most importantly, we actually want to have centroid spectra. So if I zoom in, we can see that this is only one data point. So we only have one MZ and intensity, and we don't have a full profile of this peak in mass to charge dimension. But just now, we've been using the raw spectrum. And if the raw spectrum is a profile mode spectrum, the spectral entropy does not make any sense. So a very important thing that we have to capture or cover is that we actually don't run on the raw spectra, but rather the mass list. So let's do that. So doing that, there's some exception here. That's a different thing from the visualizer, I think. Yeah, spectrum. Okay, so we're fine. That's something else. But so from the task that we've just been creating, feature spectral entropy task, in here, we can now change this method a little bit. So that first, we're going to have the mass list instead of the scan. And the get most intense fragment scan actually gives us the raw scan at first. And that's very good because from the scan we can get any kind of information like the retention time, number of raw signals and so on. But we can get from the scan, we can get the mask list, and there's always one mask list, but it needs to be processed. Like people need to call the mask detection module, and if I hit Control Alt V, I can define again a variable mask list, and this might be null. So if I look into the method signature, I can see that the return type is a mask list, and it might be null. So I do have to check in my method here if mask list is null, then I'm in big trouble. Or better, the user's in big trouble, right? Because they have to run the mask detection beforehand, and they did maybe for the MS1 spectra for generating the feature list, but there's sometimes people forget to run it on MS2 spectra as well. So if the mask list is missing, that's a very severe issue that we cannot solve in this module. And therefore, we're just going to throw a new exception. Typically, we can just use like any of this like illegal argument exception and something. You can also generate new exception types. And in MZmine, we also have a few. So we have missing mask list exception. So because that's happening a lot, or like most modules actually run on the mask list. So we can just throw a new missing mask list exception, and we can set the error message and say missing mask list for scan. We can just do this, and I think like the logging is actually going to be enough here. So it's going to log the whole stack trace, and it's going to show you what scan is actually missing. And then we can set the status of the task to task status error, and we throw a new missing mask list exception. So if we get to this point here, we're definitely going to end the run method. So we're going to jump out of the run method and back to the abstract task that is actually running all of this, and we're going to end it and end also the whole batch mode. So if someone's running this module in a batch mode and there's a missing mask list, it's going to just end the whole batch mode here, which is actually, I think, the correct way to do. And then we do the same thing, like we calculate the spectral entropy, but this time we can pass in the mask list, and we get the filtered spectral entropy basically. And everything else is the same. So, and for this, we now are like totally set. So this could already be all that was needed. Yeah. So to just recap, I'm gonna go back to the structure here, and let's just go to the module. So we only have three classes to create a new module. Most importantly, very simple, we copy the module, we just change the category, we change some like description and so on, but then we control how the task is going to be created. So how many tasks are we going to create? One for all the feature lists, or like many, like one for each. Then we define the parameters, and then the parameters are going to be like supplied to the task that actually runs a logic on a feature list in this case. And the logic, of course, because it's a very simple task, is also very simple here, right? And in this case, we're actually just running a for each loop. In Java, of course, there's different ways of constructing this. We could also use streams. So just as a little thing, we could say get rows, and then we can stream, and we could say filter, and then has MS2 fragmentation. So this is the same like a for each loop and all the things that we do, but we can like map the row to the score, we can filter. So we can first do like the has MS2 fragmentation, we can map the row that we have, so it would always be a row and then a lambda, so like a function that we want to call row. And then we can map the row to, for example, get most intense fragment scan, get mass list, and so on. Yeah. So we can map those, and then in the stream, so in this for each stream basically, we can just concatenate all these operations and pipe the results into the next step, and later, for example, map to double, and then scan utils, get spectral entropy, and so on. So if we do this, some people prefer this way of coding, right? It's very expressive, and it shows how like the flow of data works. And sometimes it's easier to just do a for each loop, especially here because we have a like if the task was canceled, it's way easier to just like break with this for each loop and just return from the whole method as if you were in the stream. And then we have some conditions here that need to be met. And of course, we can also check beforehand. We could stream through everything and just check if the mass list is actually available for all the scans that we're processing. But so if we run on this, we get the spectral entropy. One thing that I wanted to do is sometimes it's very clean because this is more like the larger scale logic that we're running, like the flow of the module, of the task. And this is actually the only logic part, right? So we could Control Alt and M, extract a method from it, and we can just say process row, and it's automatically giving us a new method where we input the row, and then we don't output anything, so it's like a void method. We just generate new data and directly add it to the row. And so we can like extract this method from there. I think this way, like the whole logic of the run method actually fits into one screen. It's very easy to see where we're going, and even for the process row, we could even, I think, make this public, and then okay, this one's like specific to this task, but we could make this public, and then someone could just call this task and process row with any featureless row from the outside, and the row would just be like get these two data types added to the row. So that's usually a way to make it more modular, so that it's reusable. Just one thing, so this would be all to process just the best, most intense fragment scan. We typically have multiple fragment scans, and the spectral entropy might be very different between those. And so if we want to get the spectral entropy of all of those, we can actually very nicely use the streams again. So let's let's maybe keep it this way, and we can just copy the method and just say process rows all scans. And in this method, we actually look at not only the best one, but we actually look at all the scans. And this time, let's get rid of some of these things here. This time, we are going to stream, no, wait, we're actually going to get the all fragment scans. So not the most intense, but all. And then from here, we can stream, and we can map each of the scans. So if I just hit Control and space, it's going to give me some options, and I want the mass list in this case. And again, we do have to make sure that the mass list is actually something. So in this case, we could do something like objects non-null. So I only have to type in minimal information, and IntelliJ usually knows what I want to do. So if I do objects non-null, this filter is going to apply to each individual scan dot get mass list, right? So we have mass lists here, they're going to be filtered, and maybe we have a remaining list of mass lists. And of course, I mean, again, I should check beforehand. I should make sure that this is actually that we do have mask lists because they should be there. It's a precondition for the whole module, so we should maybe check it beforehand. And then we have the filter, and we still have a stream of mask lists, and we just want to map this to the spectral entropy. And so we can map it to a double value and use the scan utils and then get spectral entropy. And if we now look at this, code, so we do the same thing. We have scan utils and a mask list that we fit in, and we want to now set the spectral entropy that we get. We want to set to the row type, but we only want to set one, and we might have like 10 spectra. So we need to reduce the number, and there's like different ways to do that. So we have some reduce functions here, and for the spectral entropy, let's say we want to use the minimum number, like the minimum spectral entropy, so the minimum chaos, or the maximum. So like, you can decide. So we use the minimum here, and just to show what kind of type we get. So if I just hit Control space again, we're going to see minimum actually gives us an optional double. And to show you what that is, typically we have a list of something, we stream over it, then there should be a result, right? But if we filter the list might get empty, and then we have no value. So we have to define what happens if we don't have a value. So of course we could now say like, okay, we're going to just pass in 0. But this would mean that we just set the spectral entropy to 0, which does not make any sense. Like, there is no spectral entropy. But with the optional, there's a nice way to use like some functional programming here. There's some nice way to just say, if present, apply this function. So instead of getting the value now and then checking the value and stuff, we can just say, if we have a value, we can pass in some method. So value, lambda, and then row, set, and then value. So exactly like before, we have an optional value. So either it's there or we don't have a value. If it's present, we use this value and we pass it in the row.set spectral entropy score type to float of the value, because it's double, we need to remap it. And we can copy the same code. And now just change to the normalized spectral entropy here. And of course here also like get normalized spectral entropy. And that's going to give us both these values. And of course we have to make sure that like those conditions are met, but it's a nice way of like working with streams and then reducing them to like one value, and only if we actually have a value, if all the filters basically left us with a value, we're going to apply a method to it. And then we would just change our method here and actually run on all the scans. I'm not going to do that now. It's going to be the same as before, just now like slightly different values because we use more scans. And we, maybe I'm going to run it. Let's do it. And of course, as I said, usually we set up down here. So I'm going to reprocess. We set up here for our logic, and we should do some precondition checks down here. And if we don't meet those conditions, we're going to do the same thing here. We're going to throw it an exception, or just like set an error message, set the task status to error, and then return out of this run method without completing it, right? So this should be a thing that we should actually do for the mask lists. Now, just to check, it should still work pretty fast. So we select the feature list, we run, and it's done. So this time we actually ran on all the different fragment scans. So it's like a very small data set, but it's also like a bunch of rows, and we have two samples. We have a bunch of different fragment scans here. So this is a way how you can define the module, user input, and the logic, and it's usually applied in most of the modules. Just look for the modules that are very similar to what you want to achieve, and then you can implement the logic yourself. See you next time for the next video.